In our electronics projects, we often need a DC-DC converter for various purposes, for powering our little circuits, Arduino modules or whatever. And these types of modules are ubiquitous in the marketplace. You will see them advertised. I've seen some listings which are rather confusing. These modules in particular use the Xl6009 IC as the controller. Is it buck? Is it boost? Is it boost buck? The actual chip itself can do all of those things. However, it depends on the particular design. For example, this is a boost only version, and you can see it only has one inductor, which is a telltale sign. This guy, however, that uses exactly the same chip is a boost buck. If you look at the data sheet for the Xl6009, you'll see it listed as a buck boost, or otherwise known as a SEPIC controller, that is a single-ended primary inductor converter. Easier to say SEPIC, I guess. The buck side of things is a step down. It's called a buck converter, not because it costs a buck, but because the inductor on the input bucks acts against the input voltage. So you can think of it as a bucking bronco. You have to be careful how you say that. The input range for these modules is between 3.8 and 32 volts, and the output can be set from 1.25 to 35 volts, so it's a very useful range. The little setup I have here, just to demonstrate, perhaps we have an input from a lithium-ion battery, that will be 4.2 volts, and here it's simply powering an LED and taking some 30 milliamps at 5 volts. So this is the output voltage that we've set by the potentiometer on the board. There are a couple of design gotchas with this type of module which I wanted to show you because some people are unaware of them. Assuming that this is a lithium-ion battery, okay, it's fully charged at 4.2 volts, it could easily go down to 3 volts or 2.8. What happens to our output voltage when the input voltage drops? As I said, these are designed for a minimum input voltage of 3.8. Let's just see what happens when we reduce the input voltage. So now we are below specification, but the output is staying at 5 volts. We go down a little further and something really strange happens. Suddenly the output voltage has jumped to 14 volts and it's now pulling 0.4 of an amp, which is going to kill that LED. So as we go down below 2.7, 2.8, we can see that the current drops right off, and then finally the thing drops out entirely. The reverse is true. If we go steadily up in voltage, as we reach 3 volts, again we see a large increase in the output voltage until it starts to regulate it properly at 3.8 volts as it should. We can see clearly if this was a lithium-ion cell, it could deliver that amount of current and blow your circuit to bits. We can guard against that with some sort of circuitry for a lithium cell, but these type of devices are commonly sold to be used in conjunction with solar panels, and clearly with a solar panel the voltage can go much higher, so it wouldn't be unusual for it to go up to say 6 or even 7 volts. Now that is clearly not a problem, but the reverse is true. So again, you know, if it's a cloudy day, the voltage is going to pass through at some point this danger area of around 3.3 volts. So that's just something to be aware of in your projects. In the next example, we can show another issue to do with the step up, the boost side of things, which you may not be aware of. It's very easy when you're developing a new project just to lash something together and switch it on. All of a sudden the magic smoke escapes and you perhaps haven't thought about it, haven't thought it through. Here I've tweaked the voltage now up to 24 volts. On YouTube and other places, people will then try to hook up a motor or an LED, a high power LED, and think that they can, because this is rated at 4 amps, they think they can pull 4 amps at 24 volts. Unfortunately, this is not the case. There is always a trade-off, as with everything in life. If you're going to change 4.2 volts up to 24 volts, there is a penalty to pay. And that penalty is the amount of current that it will draw. Here I have an electronic load which is set to 0.25 of an amp, a quarter of an amp. So let's see how much current that's going to draw from our power supply. And clearly it's pulling over 2 amps. So that is the penalty that we pay for boosting the voltage up. So clearly at quarter of an amp we're not going to be running motors or heavy duty things. The fan has just kicked in on my power supply here. That fan used to run all the time, but I found a solution to that. So what happens now, perhaps, if we try and go higher? Let's go to, say, 0.28 of an amp, 280 milliamps. And we start again. We can see now that we're up to 2.7 amps. Let's go for broke, 300 milliamps. And now the thing is struggling. It's over the 4 amp limit. This is getting nice and toasty, so we'll switch it off. So clearly that's the limit, the limitation of trying to generate much higher voltages from the lower voltage. Now obviously we could put a little heat sink. These come with a little sticky pad. We can put that guy on there, but in reality it's not going to solve our problem. So just be aware of that as well. There's nothing worse than a project that goes up in smoke at the first attempt.